Okay, folks, welcome back. This is still chapter 6. This is normal distribution. We are in section 6-2, and I am now starting video recording number 3. And as I mentioned to you before, this is a little bit different from your book, perhaps, because I'm using the PDF version of the ninth edition, just for convenience. Okay, so where we left off, uh, did a few of those examples. Now we're going to talk about this problem, which comes up all the time, and that is finding a data value that corresponds to a given specific probability. Does that make sense? In other words, if I tell you I want the best doctor in town, the top 5% of the doctors, how would I find that? Uh, or the people that got the best scores, the top 5% of the scores, how would I find that using a normal distribution? Well, everything comes from this original formula here. This transformation type formula, we're going from the x values to the z values. Well, here's the formula, okay? We play with that. We manipulate it. We solve for x. Okay, so can you see what's going on here? You multiply both sides by sigma. Okay, you got to take away sigma here, so we add sigma to both sides, or excuse me, a mu. We have take away mu here, so we add mu to both sides. Basically, we isolate the x on the left-hand side, and here's what we get. So what we have then is a new formula. This is a formula for finding the value of a normal variable x. So remember, x is the original formula, or excuse me, the original data point, the original measurement, whether it is IQ or the number of liters of blood. It doesn't make any difference. Whatever the original variable was, we call that x. Okay? Gosh, this is not working well. Give me 1 second here. Okay, so how do we do it? First thing we do, step number 1, we draw the curve. We draw a cartoon. We shade the area. This is to facilitate things and make sure that we understand what our problem is. And then we find the z value from the table that corresponds to that desired area. And then once we find out what that z value is, we can finish up by calculating the x value by using this formula right here. Okay, so here we go. Police Academy qualifications. And this is the same example that's in the textbook edition number 10. So we got the requirement is to get into the police academy. The various candidates, they take an entrance exam and they have to score in the top 10%. Okay, we're going to assume that they're normally distributed, and we're going to say that the police chief did this test, did many of these tests, and he came up with the population, and he calculated the mean, and he calculated the standard deviation, and that's given to you. 200 for the mean, 20 for the standard deviation. Find the lowest possible score to qualify. Now that's a legitimate question, right? I mean, if you had all this data, you'd say, I want to know what's the top 10%. You'd want to know this. So you draw the curve. Here's the curve. 200 is the mean. This is what we're looking for. We're looking for that data point x, the measurement point x, such that 10% is to the right. So what's the cutoff? Is it 90%? Is it 85%? Is it, whatever it happens to be? What is it? What's that test score? Okay. All right. So we're gonna, in order for us to find this, we have to recognize or remember that the table gives us the area to the left. So we're going to take 10% here, 10%. We take that away from all of it. That's from the 100%. So 10% is deducted from 100% to get the area under the normal curve to the left of this guy. Okay, so that's what we're looking for, is what area is to the left of this guy right here. Is 90% is to the left. So what we got to do is we got to find the value. There's no formula for that. What we do is we look in the table. So you go in the back of the book, you look in the table, you find the guy that corresponds. The closest value to 90% is to the left. And it turns out that it is 1.28. Gives you 90% to the left. Okay? Now in real life, what happens is if you do this for a living, you have some of these, you have one of these tables, printed out, and you'll circle the values that you're interested in. Like if you want 90%, you circle that value. So you don't have to look through the table. First time through, you obviously have to understand how the table works. Okay, so now we've got the appropriate Z value is 1.28. We got X is this formula here. Well, Z is 1.28. Sigma was given to us as being 20, and then mu is given to us as being 200. So you crank out those numbers, and there it is. A score of 226 should be used as a cutoff. Anybody that scores 226 or higher, they're in the top 10%, therefore they should be admitted. Okay, this is a medical example. I think I like the medical examples. Let's take a look at this one. Example 610, and that is the same as what's in your textbook. So the researcher wants to select people in the middle 60% of the population based on blood pressure. Now, can you see why you'd want that? I mean, in other words, you don't want guys that are way off the charts. You don't want people that have really low blood pressure, like, marathon runners, and you don't want people that have high blood pressure because they have a condition. So you want to have people kind of like right in the middle, so that hopefully, you can come up with some good information. Okay, so the blood pressure readings are normally distributed. The mean right here, the mean of the original data points, the original random variable, which is systolic blood pressure. By the way, systolic blood pressure, there's two blood pressures, right? There's like 120 over 70, 130 over 90, whatever it is. The top number, that's the systolic. The bottom number is diastolic. That systolic is when the heart is pumping, diastolic is when the heart is not pumping. So it's that's what the blood pressures mean. Okay, so we have 120 is the mean, the standard deviation is 8. Now we don't put the 8 in here anywhere. That comes into the formula when we calculate the Z value. So that's why you're not seeing that right here. Okay, so you draw a normal distribution curve. So this is an example of why it's so important to draw these cartoons so you can figure things out. Otherwise you'd be nuts here. So you draw the curve and you say to yourself, okay, I want 60% right here in the middle. I want 30% this away, 30% this away. The total in the middle here I want is 60%. Well, if it's 30% here, 30% here, that tells me that there's 20% over here and there's 20% over here, okay? All right, so you shade the desired areas. The desired area is at 60% right there in the middle, okay? So you need these two values. You need the x sub 1 and x sub 2 to find that. And then you find the Z values. Well, how do you find the Z values? Okay. Okay, so this is very similar to the previous example. We want to find the X value that gives us the desired result. Okay, so to find that, we need an X1 and we need an X2. So the X1 is telling me that it's 20% to the right, and the X2 is the value that corresponds to 20% to the left. All right, so to find these Z values, you just take the steps as before. Now, I guess the only nuance here that you might think, well, what the heck, where is this coming from? And let me clarify. We're going to find the corresponding guy to the X1. We're going to try to find that guy first. Okay, so what we want is this area to the left here, okay? Well, it's not, this 30% here, obviously, that's part of the area, but there's more. You go all the way to the left from the mu value as well. So you have 30% here, and then you have 50% in here. So that's why he says you add 0.50. In other words, you add 50% plus this 30%, that gives you 80%. So in other words, you want 80% to the left of this X1 guy, okay? So you find that guy. So the Z value that corresponds to this X1, that's the Z value with area to the left closest to 0.8000. Well, you look in the table, and you're going to have to verify this for yourself. Look in that table, and it turns out that that particular Z value is 0.84. Okay, so I'm going to plug that in right here. I'm going to substitute the 0.84 into this formula for X1. okay, here's my x1, is z times sigma plus mu, so it's 0.84, that's what I just found, times 8. 8 is my standard deviation. That was given to me up here, standard deviation 8. Okay, so everything's just plugging it in. And then the 120 was also given to me. So what that's telling me, you crank out these numbers and you get 126.72. So if x sub 1 is 126.72, what that's telling me is that 20% will be to the right, 80% will be to the left. Okay, all right, so that takes care of x1. The area to the left, I'm sorry, I had a technical problem. The area to the left here of this x2, this area that I want right here, is 20%. Well, I don't have to do any of this first step. I don't have to add the 50%. It's, again, these cartoons just tell you everything. This area right here is 20%. What value of z corresponds to that? What gives me a 20%, like right here? Well, that number is negative 0.84. So plugging it into the formula is negative 0.84 times 8. You know, I'm using this formula right here. Negative 8.4 times 8 plus 120. Crank that out, is 113. So this guy right here is going to be 113.28. This guy right here is going to be 126.72. So the middle 60% will have blood pressure readings between 113.28 and 126.72. You see how that notation works here? X is greater than the 113, but X is less than the 126.72. Okay. All right, so I mean, as you can easily see, this normal distribution is used all the time. It's just very, very common. I urge you to just Google it, on your phone or your computer. Just Google normal distribution uses or uses of normal distribution, and you'll see a bazillion examples. If you look in the exercises, you'll look and you'll see a bazillion examples. Okay, I'm almost out of time, so I'm going to stop this recording and I'll do one more recording to finish up this section.